Good day, Ms. Barber here. We continue with our study of statistical reasoning. This lesson is called Correlation and Causality. The learning objectives for this lesson are: be able to compute and interpret correlation, be able to construct and interpret scatter plots, be able to identify types of correlation, be able to provide explanations for correlation, be able to apply guidelines for establishing causality, be able to compute and interpret confidence in causality. Correlation. A correlation exists between two variables when higher values of one variable consistently go with higher values of another variable, or when higher values of one variable consistently go with lower values of another variable. Important note: correlation does not imply causation. Examples of correlations. There is a correlation between the variables height and weight for people. That is, taller people tend to weigh more than shorter people. There is a correlation between the variables demand for apples and price of apples. That is, demand tends to decrease as prices increase. There is a correlation between practice time and skill among piano players. That is, those who practice more tend to be more skilled. Scatter plot. A scatter plot is a graph in which each point represents the values of two variables. Note, the scatter plot is only the points. More importantly, do not connect the points. Relationships between two variables. No correlation. There is no apparent relationship between two variables. For example, there is a 100% relationship between those who have died and those who have breathed at one point. However, it would be very wrong to say that breathing causes death. Positive correlation. Both variables tend to increase or decrease together. For example, the more I work out, the better fit I get. Negative correlation. One variable increases while the other decreases. For example, the more I watch television, the less productive I become. And strength of a correlation. The more closely two variables follow a general trend, the stronger the correlation. In a perfect correlation, all data points lie on a straight line. Example of a positive correlation. Consider the cost of diamonds. A scatter diagram shows that higher diamond weight generally goes with higher price. The graphic depicted shows the weight in carats of the diamond along the horizontal, starting at 0 and increasing in 1/2 increments to 2.5. The vertical axis on the left gives the price in dollars, starting at $2,000, increasing in $2,000 increments to $16,000. While there are a few outliers, the general trend is higher the weight, higher the cost. Let's consider an example of a negative correlation. A scatter diagram shows that higher life expectancy generally goes with lower infant mortality. This graphic is titled Life Expectancy and Infant Deaths. Along the horizontal, it is labeled Life Expectancy in years, and it starts at 50, increases in 10-year increments to 80. On the vertical is infant mortality, and death per 1,000 live births begins at 0, increases in 20-unit increments to 120. We see that the lower the infant mortality is related to higher life expectancy. Example: accuracy of weather forecasts. The scatter plots show 2 weeks of data comparing the actual high temperature for the day with the same day forecast, which is the left diagram, and the 3-day forecast, which is the right diagram. Let's discuss the types of correlation on each diagram. Each of the displayed scatter plots on the horizontal states what's happening. On the left, it says same-day forecast and degrees Fahrenheit. And along the left, it is vertical, actual temperature starting at 20, increasing in 10-degree increments to 70. The right scatter plot is the 3-day forecast, and along the horizontal, it's from 20 to 60, and the actual temperature along the vertical is 20 to 70 in 10-degree increments also. Analysis. Both scatter plots show a general trend in which higher predicted temperatures mean higher actual temperatures. That is, both show positive correlations. The points in the left diagram lie more nearly on a straight line, indicating a stronger correlation than in the right diagram. This ought to make sense because we expect weather forecasts to be more accurate on the same day than 3 days in advance. Possible explanations for a correlation. 1. The correlation may be a coincidence. Let's look at the site http://www.tylervigen.com. Some of these are called spurious correlations. For example, we see a pretty strong correlation between divorce rate in Maine and per capita consumption of margarine. We can all conclude those two are not related. How about a correlation between math doctorates awarded and uranium stored at U.S. nuclear power plants? Both of these were examples of spurious correlations. There's no underlying cause, it's just that it's coincidentally correlated. 2. Another possible explanation is that both variables might be directly influenced by some common underlying cause. For example, consider ice cream sales and the sale of sunscreens. They seem to be related, but we know that one doesn't necessarily cause the other. That is, buying ice cream doesn't cause a greater sale of sunscreen. However, there is a common underlying cause. And what is that? Increase in temperature. And 3, one of the correlated variables may actually be a cause of the other. Note that even in this case, it may be only one of several causes. For example, consider cigarette smoking and incidences of lung cancer. Example, explanation for a correlation. Consider the negative correlation between infant mortality and life expectancy. Which of the 3 possible explanations for a correlation applies? Answer. The negative correlation is probably due to a common underlying cause, the quality of health care. In countries where health care is better in general, infant mortality is lower and life expectancy is higher. Now on to guidelines for establishing causality. 1. Look for situations in which the effect is correlated with a suspected cause, even while other factors may vary. 2. Among groups that differ only in the presence or absence of the suspected cause, check that the effect is similarly present or absent. 3. Look for evidence that larger amounts of the suspected cause produce larger amounts of the effect. 4. If the effect might be produced by other potential causes besides the suspected cause, make sure that the effect still remains after accounting for these other potential causes. 5. If possible, test the suspected cause with an experiment. If the experiment cannot be performed with humans for ethical reasons, consider doing the experiment with animals, cell cultures, or computer models. And 6, try to determine the physical mechanism by which the suspected cause produces the effect. Case study: airbags in children. By the mid-1990s, Passenger side airbags had become commonplace in cars. Statistical studies showed that the airbags saved many lives in moderate to high-speed collisions, but a disturbing pattern also appeared. In at least some cases, young children, especially infants and toddlers in child car seats, were killed by airbags in low-speed collisions. Let's do some analysis. At first, many safety advocates found it difficult to believe that airbags could be the cause of the deaths, but the observational evidence became stronger, meeting the first 4 guidelines for establishing causality. For example, the greater risk to infancy child car seats fit Guideline 3 because it indicated that being closer to the airbags increased the risk of death. A child car seat sits on top of the built-in seat, thereby putting a child closer to the airbags than the child would be otherwise. To seal the case, safety experts undertook experiments using dummies. They found that children, because of their small size, often sit where they would be easily hurt by the explosive opening of an airbag. The experiments also showed that an airbag could impact a child car seat hard enough to cause death, thereby revealing the physical mechanism by which the deaths occurred. Confidence in causality. Possible cause. We have discovered a correlation, but cannot yet determine whether the correlation implies causality. In the legal system, possible cause, such as thinking that a particular suspect possibly caused a particular crime, is often the reason for starting an investigation. Probable cause. We have good reason to suspect that the correlation involves cause, perhaps because some of the guidelines for establishing causality are satisfied. In the legal system, probable cause is the general standard for getting a judge to grant a warrant for a search or wiretap. And finally, cause beyond reasonable doubt. We have found a physical model that is so successful in explaining how one thing causes another that it seems unreasonable to doubt the causality. In the legal system, cause beyond reasonable doubt is the usual standard for conviction. It generally demands that the prosecution show how and why, essentially the physical model, the suspect committed the crime. Note that beyond reasonable doubt does not mean beyond all doubt.